So, section 8.2, we're looking at modelling assumptions, and really, there's sort of three things to think about here. First of all, there's a whole bunch of new vocabulary that you need to get used to. It won't sink in at first. When it will sink in properly is when you're starting to apply these words, and that is in the later chapters. So you're going to need to look at this initially, try and get used to the ideas, and then look at the later chapters and come back and make sure you know what it means when they're saying it's a smooth surface, it's a smooth and light pulley, those sorts of things, okay? Secondly, they are quite keen at the moment on the exam papers for asking you some justification of, what were the modelling assumptions you made in this question, and how do they affect the question. On maybe 70% of the time they ask you that, you can get away with just quoting exactly what it says in this textbook. Not always, but a lot of the time, you can say, well, we had a car, we modelled the car as a particle, and what happened there, it meant that we could ignore air resistance. Okay, so this table, by the time you hit the exam, really is something that wants to be second nature and memorised. Now, if you look at that table, there's a lot of words in there, so me saying you need to memorise that seems quite daunting, but you'll be so used to using these things by the time you hit an A-level exam, it won't be a great deal of extra effort. But the sort of thing you want to memorise is things like, if there's a particle, there are 2 points that you need to make, right? The mass is concentrated at a single point, and we're ignoring rotational forces and air resistance. If it's a rod, it's these three things that you need to know. It's those 3 points that you might need to make, and they might be asking you to make the first one or the second one or the third one. You need to look at the context of the question, see which one's important. So you need to, when you're preparing for the exam, if you've got a smooth and light pulley, that phrase smooth and light pulley tells you two things, and those two things are these two things. Okay, so you just need to do that at the last minute, and that's passing exams. Let's think about what we actually need to know here then, what's important. So firstly, this will make sense later on. Secondly, memorize it for an exam. And thirdly, just get used to these words, get used to kind of what they really mean, and get a feel for the sort of thing we're doing in the modelling. So I'll try and talk you through a few of these, and I'll attempt to make it. This is the sort of discussion that we could spend ages over, or we can do it reasonably quickly, and then you get the idea later on. I'll try and draw a line between those two things. So first of all, we need to get used to this idea of particles and rods and laminas, because what we're really doing is ignoring dimensions. Okay, so we know the idea. If you've got a three-dimensional object, say a cube, it's got three dimensions because it's got length and width and height. Okay, oops, there we go. So it goes all three directions. Now, if we've got a square, it's only got two dimensions. It's got length and width, up and down, left and right, okay? Now, if we've got a line, it's just got up and down. There's no left and right to it, okay? So it's one dimensions. The problem we've got here is that you can't actually ever see a line, okay? If I draw a line on a piece of paper, the only reason you can see it is because it has got a bit of width. There's no such thing as a two-dimensional shape in the real world, because even a piece of paper, which is almost two-dimensional, is very, very thin, but there is a width there. So when we're talking about something as having one dimension, all we ever do is draw a rough approximation of that, okay? We've been doing that for years, and it's never bothered us before. There's no reason it needs to start bothering us now. But when we say here a rod, what we're saying is let's say we've got a bead on a rod. So there's a bead with a hole through the middle of it, and it's strung on a rod. A rod, it says, the mass is concentrated along a line. There is no thickness, and the rod is rigid. So what we're saying by no thickness, you can't physically have something that's got no thickness, but we are modelling something such that the thickness of the rod compared to this bead is unimportant, okay? It's small enough that we're not going to worry about the thickness of the rod. If we're saying it's a light rod, so we're ignoring the mass of the rod, we're ignoring the weight of the rod, then we're saying that compared to the bead, the rod is so light that we can ignore it, okay? So the situation we might have, and we have quite a lot, is a pendulum. And this is for later on in the course, really. It's not in the first year, but just to give you the idea. Now, if we've got a pendulum like this and it's swinging backwards and forwards, we will often make the assumption that the mass of the pendulum is all in the weight at the bottom, and we'll ignore the weight of the, whatever it is, this chain or the string or even a rod that's actually swinging backwards and forwards. Now, if you think about a pendulum and a clock, that makes a lot of sense. There's a big heavy weight at the bottom, and there's a light, comparatively light thing making it swing backwards and forwards. As long as the mass of the string is more or less nothing compared to this weight, that's a good mathematical assumption, okay? So when we're dealing with rods, laminas, a lamina is, you can think of it as they say a sheet of paper here. I like to think of it as a sort of thin sheet of glass or perspex. It's sort of it's a two-dimensional surface. We're going to ignore the width of it, okay? So a sheet of paper or a very thin sheet of perspex, something like that. So we can have a lamina, which would be like a flat thing, a rod, which is a straight line. The thing that we use the most often here in this book is a particle, and let's just talk a little bit more about that. And I think most of the rest of this, I'm going to leave you to read through it for yourself, because I'm just going to be repeating what it says in the book. But a particle, it's saying the mass of the object is concentrated at a single point, and rotational forces and air resistance can be ignored. So let's think about a football or a soccer ball, if you like. It's not true that the mass of that object is concentrated at a single point. So a point, by the way, we normally draw as a dot. That is something that doesn't have any dimensions. So it's not got length, width, and height. It's not even got length and width. It's not even got length. It's just a single point in space. Okay, so there's no dimensions. It's not true that a football has all its mass concentrated at a single point, but there is the center of mass of the football, which would be, if it was a perfectly symmetrical football, would be right in the middle. And when you kick the football, if you kick it straight, as in there's no spin on it, it will move in a parabola shape through the air. The thing that's making the parabola is the center of mass of the football, okay? Now, in that situation, the fact that the mass of the object is concentrated at one point, that's a pretty good assumption, right? We're happy with that. It's even better if it's a golf ball, because then it's a little ball with one center of mass in the middle. That's a pretty good assumption that it's going to move as though just moves in the same way as the center of mass. Now, the rotational forces and air resistance, that's a more interesting one. If you take a football and you kick it so that it spins, then it's and now the clock's chiming, excuse me. So if you kick a football and you kick it so that it spins, then it's not going to move straight in the air. It's going to curve through the air. So if your goal's there, you can kick a football here and it will curve, wherever you're sending it. Anyone that knows me knows that is absolutely the limit of my football knowledge as well. Now, the reason it does that is because it's been kicked so that it's spinning through the air, and that means that the air resistance is having an effect, okay? The friction between the air molecules and the football is changing the path of the football, okay? So if the football was a particle, it wouldn't be able to be, well, it wouldn't, there's nothing to spin. It's a single point. The football can only spin because, that if it's going that way, then this bit's moving up and this bit's moving down around the middle, okay? If there is no piece on this side and piece on this side, if there is just a single point, then it can't possibly spin around, okay? So we can ignore sort of curving motions and spinning balls and things. If I kick something that way, it's going to go whoop, like that in a perfect symmetrical parabola. So we can ignore rotational forces, we can ignore air resistance. The other thing with air resistance, of course, is that if I were to kick, think about a shuttlecock in badminton, or if I try and throw a piece of paper through the air, it's not going to go like that. It's going to, because there is so much air resistance, the molecules in the air are pushing back against the object that's moving through the air, and that's going to slow it down. So if we're looking at a particle, we're assuming that something that we can model as a particle will be something like, something fairly massive as a pen or a stone, something like that, so that when I throw it through the air resistance is small enough compared to, there's always going to be some air resistance. It's always going to get slowed down slightly, but we can ignore it because the slowing down effect of the air resistance isn't going to materially affect our predictions or our models. So if I throw a stone through the air and I ignore air resistance, if I model it as a particle, I can predict where it's going to land depending on how hard I throw it and where I throw it from. If that prediction is close enough, say it's within a centimetre or two, or even within 10 centimetres or so, that's a pretty good prediction. That's close enough for our reasons, okay? If I throw a piece of paper through the air and I ignore air resistance, then that's not going to work at all, because air resistance has such a big effect that it's not going to work. If I take a piece of paper and I crunch it up into a ball, then ignoring air resistance is better, because the air resistance isn't going to affect it as much when I throw it through the air, but it's still going to make some sort of difference. So modelling a stone as a particle is much better than modelling a piece of paper as a particle, but I might still want to model a piece of paper as a particle. Maybe that's going to be useful to me somewhere, okay? Now just having a quick look down here. So we've dealt with particles. I think the rest of these are things that we can get used to later on. Smooth surfaces is where we're going to ignore friction, and a rough surface is where we're going to take account of friction, and we're basically going to ignore friction until the second year of this course, so that's nice for us. Most of the rest of them sort of make sense. I think the last thing is to think about having a light pulley, and the rest of these I'm going to leave to you to read the information for yourself, and then that will also make sense in context of the chapters. But let's just have a think about a pulley first of all. So a pulley could be like this, and a rope's coming up on this side and going down on this side, and let's say the pulley's fixed onto the ceiling like that. So it's important that this is smooth, because if you imagine if there was some friction on this, if you imagine you got an old pulley and it was really sort of rusted up and it was high in friction, then the rope wouldn't slip smoothly across it. Okay, if there was a lot of friction going on around the axle of the pulley, say, or between the rope and the pulley, then you might not even be able to move it around at all. So we're saying that this pulley is sort of, if you've got a nice, well-oiled pulley and the rope is smoothly pulling around it, then that's a good assumption. And when we've got pulleys, that's the sort of thing we're tending to model. We'll have a weight on here and we'll have a weight on here, and the whole thing will be slipping one way or the other way. So that's why the no friction is important. The other thing is, imagine you got a pulley like this and you stuck a huge weight there, like a really big weight, something really, really heavy. Then this wouldn't rotate in a smooth sort of way, would it? It would be really hard to pull this up to the top, and once that got to the top, you got a really big heavy weight here, it would shoot back down to the bottom again. So when we're ignoring the mass of the pulley, when we've got a smooth light pulley, what it means is the rope is going to move over the pulley in the way that we want it to. The pulley is going to work like a pulley, and that's why we need to ignore the friction and why we need to ignore the mass of the pulley. As I say, the rest of these things, once you've got those ideas in your head of ignoring air resistance, ignoring friction forces, hopefully reading these assumptions will make sense for you. And if not, do the rest of the chapters and then come back and it will make a little bit more sense. Or, of course, talk to your teachers face to face.